In this video, I will discuss and introduce the concept of Taylor and Maclaurin polynomials, and later we will see some interesting applications of these constructs. But first, let's recall the following development from before. We said for some function that has all the derivatives, we can create the series using the following formula or a way, and such series is called Taylor series of this given function. And we haven't proven it yet, but it would be nice that the Taylor series, when converges to this given function from which it was created. And similarly, we have what we call Maclaurin series, which is the same as Taylor series, but we say the Maclaurin series are centered at 0. So by simply choosing C to be equal to 0, we will create what's called Maclaurin series. And every function that has all of its derivatives can generate such series. And previously we also discussed the applications of such series, and in all of those applications what happened is that we were or at least in many of them, we were writing out some of the terms of the power series, and then we would just stop and we will write ... because, as you know, it is impossible to list all infinitely many terms of the series. And we usually wave our hands and we would say something like, well, we would write as many of these terms as we need for this particular application. Because there are infinitely many, we have infinitely many to dig into. However, this process of cutting out the power series can be formalized. So, for example, I can, when we write this Maclaurin series and we write it out like this, and then at some point we decide to stop, so it may not be 3, so let me just write a few more. I may stop at kth term. So the kth term, it's the one with the coefficient a sub k and x to the power k. Well, what we have created by just truncating the series actually has a name, and it is called Maclaurin. In this case, Maclaurin, because we started with Maclaurin series, but it will be called Maclaurin polynomial of degree k, and it will be labeled as m sub k x. And formally, what's going on here is that we're taking our Maclaurin series, which can be written like this. And we're separating it into 2 parts. So we're taking all the terms up to power k, and we take all the terms after that. So that will start with k plus 1 all the way to infinity. And we're calling the first part of this expression, so the one that embeds the first up to kth power, and we're calling it the Maclaurin polynomial of kth degree. So k could be any number. And in this case, again, what makes it Maclaurin is how we find this coefficient. So the nth coefficient can be found by evaluating nth derivative at 0 and dividing by n factorial. So previously, when we just waved our hand and said, hey, well, we can write as many as we need, now we have a formal name for it. So instead of saying, let's write first 10 terms, we can just say, let's consider the Maclaurin polynomial of degree 10. And now what's left after you take your first kth powers, including the 0th power, is called the remainder. So the tail of this series is called the remainder, and it's labeled as RKX. So the remainder is also a series because it contains infinitely many terms, but we're going to refer to it as the remainder. Now, just like this, we can define the Taylor polynomial for of degree n for any function. So let me just show you what it's going to look like, right? So instead of x, or I guess even here, we need to specify that nth term is equal to the nth derivative evaluated at 0 over n factorial. Now, if we take this definition and simply, instead of x, write x minus c. So let me just remove all of this. So if instead of x, we'll write x minus c. And if we do ... here, and then we'll put, this is the kth coefficient, and x minus c to the power k, and etc., then this so yes, we don't need this plus ... right? So this is not going to be Maclaurin polynomial. This is what we will refer to as Taylor polynomial of degree k. And if it's a Taylor, then we also have to specify where it's centered. So we would say Taylor polynomial of degree k centered at x equal c. And instead of letter m, we'll be using letter t. But everything else pretty much remains the same. So now, instead of having all these coefficients evaluated at 0, we're going to have them evaluated at c, and we're going to have x minus c to the power n. And here as well, the tail or the remainder of this series will contain x minus c, and we're going to call this tk. And whenever we're dealing with tk, we have to specify where it's centered, and this particular one is centered at c. And one thing that we do have to mention here is that if we consider the entire series, then there is an equal sign there. If we don't consider the entire sequence, we cannot put the equal sign here anymore, right? So either we're going to have to put approximately equal to here, or a better way will be to acknowledge that f of x just creates this context, but whatever we wrote here is actually my Taylor's, or in this case Maclaurin's, polynomial of degree k. So that's what this is called. And in this case, the same thing, f of x creates the context. So we do have some f of x in mind, but whatever we have written here, it's the Taylor's polynomial of degree k. But if you consider the Taylor's polynomial of degree k along with the remainder, then together they can be said to be equal to f of x. And this is how we define the Taylor and Maclaurin polynomials. And the next task will be to just practice actually creating and working, like creating the polynomials and recognizing the notation, that sort of thing. And let's do the first exercise. So let's find M5 for the following function. And to do that, we're going to recall the fact that arc10x has the following power series representation. And we're just going to plug in different values of n until we generate the polynomial of degree 5. And m5x will be equal to, and let's start with n equals 0. We have 1 times x. When n equals 1, we have minus 1/3 x cubed. And when n equals 2, we have plus 1/5 x to the power 5, and we are done. So now we have a formal way of actually not to worry about this, what we would call plus ... right? So we truncated this power series and we ended up with what we'll refer to as Maclaurin polynomial of degree 5. And of course we can write that polynomial in standard form, but at the same time it is not necessary. Let's find the Taylor series. Let's find T6 for sine of x centered at pi over 4. And to do that, we're going to use the Taylor series, the formula for the Taylor series that says that the nth coefficient is equal to the nth derivative evaluated at c divided by n factorial. C in this case is pi over 4. And let's get started. So to find the first coefficient, or rather the 0th coefficient, we have sine of x. We evaluate sine of x at pi over 4, so we get square root of 2 over 2, and therefore the 0th coefficient will be equal to just square root of 2 over 2. And let's continue. And the first coefficient will also be square root of 2 over 2. The second derivative is negative sine x. So this one will be negative root 2 over 2. So the second coefficient will be negative square root of 2 over 4, because we're dividing by the 2 factorial. Continuing the process. And the third coefficient will be negative root 2 over 2, but we're dividing it now by 3 factorial, which is 6, so it's negative root 2 over 12. So the fourth derivative will be back to sine of x. I may need some space over here, so let me just move this formula out of the way. And we get root 2 over 2, so we're dividing by 4 factorial here. 4 factorial is 4 times 3 times 2 times 1, so it's 24. So we have negative square root of 2 over 48. So the fifth derivative will be cosine of x. So the fifth derivative at pi over 4 will be root 2 over 2. So we're going to divide by 5 factorial here. 5 factorial is 120. So this is going to be we're going to have square root of 2 over 240. And finally, the sixth derivative will be negative sine of x again, and the sixth derivative evaluated at pi over 4 is negative root 2 over 2. So the sixth coefficient will be that divided by 6 factorial, which is 720, and we're going to have negative root 2 over 1440. And we did find up to sixth coefficient, which is all we need to construct the Taylor's polynomial of degree 4, or sorry, rather 6. So the final answer will be T6 of x is equal to, and let's write it out, square root of 2 over 2 plus square root of 2 over 2 x minus pi over 4 minus square root of 2 over 4 x minus pi over 4 squared minus square root of 2 over 12 x minus pi over 4 cubed plus square root of 2 over 48 x minus pi over 4 to the power 4 plus square root of 2 over 240 x minus pi over 4 to the power 5. And the last one, to make it a polynomial of degree 6, is just need a little bit more space over there. So polynomials of degree 6 are certainly not the easiest ones to write out, but you have to agree that dealing with a polynomial requires nothing but the ability to multiply. We don't even need to divide, multiply, add, and subtract, while dealing with sine function requires knowledge of trigonometry. So we were able to construct a polynomial, Taylor's polynomial of degree 6 to this function centered at pi over 4, and we learned the definitions of Taylor and Maclaurin polynomials and how to find them in this lecture.